So its circuit would be something like this. We will have some switches. We will do operation on switches such that it will, you know, get us the desirable kind of output waveform of voltage as well as currents. And these circuits will have some inductors and capacitors. We will discuss what are the purpose behind connecting inductors and capacitors. And there will be some load which will be supplied. Okay? And certain parameters which is generally defined here. First parameter is duty ratio. Right? So duty ratio is nothing but it is denoted as D, and it is the ratio of your switching pulse turn on period of your switching pulses. How much time that switch, any particular switch is turned on for a particular time period. So let me define it. T is nothing but T on by T, and let me draw some graphs so that we will get better understanding. So let us suppose you have supplied DC voltage. You have constant DC voltage. Okay, that is the now this switch, it will get turned on and turned off quite frequent, right? In one time period, at least once, and generally it is turned on at least once in a one time period. It's up to you how many times you want to turn it on or turn it off. That will increase the frequency, the number of times you will apply the switching pulses to the switch. So that much will be the frequency of the circuit, whatever we are seeing here. So let us suppose this is VL. Uh, if this switch is on for a particular condition, let me copy the circuit. Yeah, so if the switch is on, then whatever the voltage you have applied at input, the same voltage will appear at this node, right? And if this voltage will be at this node when the switch is on, this diode will be off, right? Since this diode will see the positive voltage across its cathode terminal, so it will be turned off, and we can conveniently remove this. Now you have certain load that will draw certain current. Okay, whatever current will go from input side, we will call it IL just for time being, and the characteristics of this IL would be such that if V naught is less than V, then your inductor will be charged, right? So, and since we are discussing about buck converter, right? So V naught will always be less than V. So this VL will see VL during turn on. It will see the voltage if you apply KVL in this loop, V in minus VC or V in minus V naught, right? And VC is equal to V naught. The purpose behind connecting inductor and capacitor is just simple to remove the ripple, right? The inductor is here to remove the ripple from the inductor current. Okay, we want a smooth inductor current like DC inductor current. We do not want any ripple. I will plot the graph of inductor current, and then you will observe that it is kind of not constant. Okay, it will be charging and discharging. So let me tell you its characteristics will be something like this. Okay, first it will charge, and then it when it will see the negative voltage across it, it will get discharged. So we will plot that curves as well. Fine. So that was it during turn on. And if you see for turn off period, okay, so this switch is open, right? Now the inductor has been charged already. Now it will see the voltage if you apply the KVL again. So let me write that VL during off condition. What voltage it will see? Anybody, please?
minus V naught.
Minus V naught. Perfect. So it will see minus V naught. So now you can see that negative voltage across the inductor is appearing, and due to this, it will start discharging its energy across the load, right? And capacitor as well. So we have computed two
Sir, can you
conditions.
explain how it is minus V naught? Can you
Huh.
explain how it is
Okay, yeah,
minus V
yeah.
naught?
Sure, sure, definitely. So if you apply here the KVL, right, in this loop, so apply KVL plus VL plus V naught is equal to zero, right?
Sir, how the diode is forward biased?
Huh, yeah, that's true. See, during this period, right? During this period, this inductor will have to discharge its energy along the V naught, right?
Yes.
Or whatever load is there. Now, to which path it will follow? Here it is a
So in order,
diode.
yes,
Huh. Yeah, go ahead, please.
yes, in order to follow that path, the diode should be forward biased.
Yeah,
But VL is having the positive side. What is making the diode forward biased?
okay, okay. So your question is that here positive terminal will appear. You
Yes,
want to say that? Okay.
yes.
So as as you might have studied in rectifier also, what was the purpose of freewheeling rectifier there?
Freewheeling rectifier.
You haven't heard of this term? Freewheeling rectifier?
No,
Oh, sorry, freewheeling
no.
diode.
Yes, sir, I don't want freewheeling data. I want to understand this point, how it is going to be forward biased, the diode.
Yeah, see, uh, you are seeing only this terminal, this node, right? You are not
Yes.
seeing this node. When the current will flow in this direction, the drop will
Mm.
happen in this manner, right? You agree on this or not?
See, if it is a resistor, yes. If it is a diode, the negative part should be more negative, positive end should be more positive. Then only it will be forward biased.
Okay, okay. So we will take this issue a bit later. Okay, just let me draw the graph. Till then, if you have the same doubt, we will clarify this, right? If it is okay to you.
Because this point only the turn off explains. Otherwise, we cannot go forward, right?
Okay. You want to say this point, turn off.
How the diode is going to be forward biased is my
Huh,
question.
that's I understood.
Hmm.
I am not able
Even
to
the
explain
voltage.
you. Yeah,
uh,
yeah. Your point is valid. I am not denying your point. Your point is
hmm,
very valid. But
hmm.
at this point, with the concept of freewheeling diode, I am not able to explain you, right? Because you are seeing only the positive term, positive node and negative node. So just wait till I plot the graphs, and if you have your doubt till that point, we will clarify this again.
Okay,
Is
sir.
that okay to you?
Okay, sir.
Okay, thanks. So yeah, let me plot the graph here to better understand. And another point is, if you are watching like that, see, generally these converters, they had to be supplied from some gate driver circuit, right? Or some kind of drive circuits where you inject the pulse, right? This this switch, whatever it is, thyristor or something, whichever switch you connect here, that will not just get turned on by seeing this forward voltage. They will have some, supply drive kind of supply there. It will latch the device, and then generally circuits get turned on. But anyway, we will see it again. Do not worry. So what I was telling, VL, if you see the graph of VL, then you will be confident that why it is happening like that. So during turn on, when switch was on, VL was V in minus V naught, right? Since V in is greater than V naught, so it will be positive. Now your VL is becoming minus V naught, right? Are you able to observe your answer? Who asked that question?
Yes, sir. I asked.
Rahul. Yeah,
Uh,
yeah.
yes.
So this VL you are seeing as a positive, right? But actually VL is what? Minus V naught, right?
So this you are explaining from the graph. What about from the circuit analysis?
Okay, so let us see the circuit here. This VL from circuit also, this VL will be what?
VL is V naught.
VL is minus V naught
No, VL is V naught.
from this circuit.
Yes.
How come?
Because the diode will not be turned on. VL is positive. If you apply, it is going to be
Yeah,
V naught,
when
not minus V naught.
see, okay, you are saying that diode is not turned on till this point. That's what you are saying?
Yes. Yeah,
Okay.
if you want to turn on the diode, then the voltage reversal should take place.
Okay, let's assume that both diode and switch is off. Okay. I am assuming both diode and switch is off. Okay.
Okay.
Huh. Now you tell me the voltage along this VL
Minus V naught.
minus V naught, right?
Yes.
So when switch is off, then voltage across this inductor you are saying minus V naught. So why you are saying when we are connecting, when diode is present here, it will not see minus V naught?
Sir, the positive end of the VL is connected to the V naught, right? If you apply
That,
KVL also,
that,
it
that,
shows
that
VL
is,
is equal to V naught.
yeah, that is just, notation. That is not exact value. Positive is connected. That is positive of VL we are taking as a reference. You just, we are denoting with this kind of signs here. You just
So
remove
here
this
also,
kind of.
when the switch is
Sure.
turned on, you will say plus and minus, V in minus V naught for VL.
Uh-huh. Yeah. That's correct. Yeah. And that
Yes.
Vn minus
So
V0 was positive because of the reason you have higher value of Vn.
yes.
So can we say it this way that we are the anode, cathode of the terminal when it is connected to VL? I mean, that particular point, we are
Yes.
treating that as positive for multimeter measurement.
Yeah,
Kind of.
I told the same that it is for reference. You can
Correct.
say
So, so in that case, I mean, when the capacitor is charged to V naught and there is the switch is off, then definitely whatever is the measurement here is going to be minus V naught then across VL.
yeah, yeah, you are correct. That's what I am trying to explain in other
So
words.
where is the question of diode turning on here? The negative
So,
part of the
no, there is
diode
no
should be more
question.
negative, right?
I don't think
See,
there is a
When
question of turning off the diode, on or off the diode. But if you look at
without
the
diode turning
potential,
on, you cannot show the freewheeling action here. Where is the stored energy of the inductor is going to be dissipated without turning on the diode? That is the question, right?
Mhm.
Huh.
see, uh,
Sir, answer me.
yeah, yeah, yeah. Go ahead. If you want to tell some more, you can go ahead.
No, no, I've already told how the diode is going to be turned on in this
Huh.
case.
Yeah. So I just try to explain with this kind of scenario. You are
So let us
assuming
take the
that,
circuit
Sir,
analysis and explain it.
sir,
yeah, Muthu, you want to say something?
yes,
Yeah,
sir.
go
Actually,
ahead.
what he is expecting is that Rahul Jagan. I think is we want to know how this inductor, how this diode is turning on during the off state of the switch. Sir, actually, at that time, the voltage across the inductor should be higher than the output voltage plus the voltage sufficient to turn on the diode. That is the amount to which this inductor voltage has risen during the on time of the switch. We should make sure that the voltage has reached to a point during on time of the switch that it reaches the value which is equal to output voltage plus the voltage sufficient to turn on the diode during off time, so that when you open the switch, the voltage across the inductor will reverse. That is, the left side become negative and the right side will become positive because the current through the inductor is now decreasing. So
Okay.
because of that, the voltage reverses.
Hmm.
So that which means now the left side becomes negative and the right side becomes positive. Now
Mhm.
now the inductor is a source. Now it is
Yeah.
dissipating the energy which it has accumulated during on time. And now that since that is left side of the inductor is negative, right side is positive, that potential is the output voltage potential plus the voltage required to turn on the diode. In that
Yes.
way, it
Then VL is equal to V naught, not minus V naught.
no, because that
Yes.
because this is yeah, VL equal to V naught, but the
Hmm.
reference we have taken is left side is positive, right? As sir said, Sanjay Patil sir said, left side is positive, right side is negative. That is, we are connecting the multimeter positive probe to the left side of the uh, left side of the inductor, and the negative and the reference probe, that is the black probe of the multimeter, to the right side of the inductor. So it shows minus V naught. That is the reference we are taking. We
Yeah.
can't change the multimeter probe for each cycle. We will keep the multimeter probe at a fixed
No,
point.
leave about the multimeter probes. Let us not concentrate on
Because that is a
multimeter probes.
reference.
What
Because
about the circuit analysis? VL is equal to V naught, right?
Okay. So let us have this conversation at the end of the session if you are not convinced, Rahul. But as of now, what I can explain, if you are taking this reference, you want to assume that VL is equal to minus V naught, fine. You can assume that, right? But the thing is,
VL is equal
even
to V naught.
VL is equal to V naught if you want to assume.
yeah, with
But
this reference,
with
with
this
the
reference,
current
but
polarity sir have drawn, now
see,
VL equal to V naught.
generally in
Yes.
any any sinusoidal kind of source, they do not have any sign, right? They are kind of variable magnitude, but they are denoted as some plus minus. Why? Just to take as a reference. The point of reference is only here that you are not getting. So anyway, if we are not, you know,
No,
agreeing on this,
because this end, the left end of this one is at zero potential, or there is no potential, right, in the inductor.
in the
It is
inductor,
lower.
yeah, yeah,
Yes,
of course.
yes. Then the
Yeah.
sign convention is correct, right? Minus
Uh,
and plus.
Now whatever
Then
you
VL
are,
is equal to V naught.
yeah,
Hmm.
yeah. Now whatever you are watching, you are convinced with this, right?
I'm not convinced. Then VL is equal to V naught means the graph will not be valid. It will not
Huh.
come down.
Yeah, you do not worry about graph now. You are
Hmm.
convinced with this denotation in this circuit, right?
Yes.
Yeah, fine. So
But why they will write VL is equal to minus V naught when the switch is turned off?
eh, that's what we are trying to convey, that we are taking as a reference. Let's assume with this convention, if you are taking this, you are fixing this convention once and you are stick to this once, then you cannot change this convention every time. Otherwise, it will be too much difficult to plot all the graphs, right? We have fixed this convention once, and now we are sticking to
No,
this
sir, you cannot
convention,
fix the convention for the inductor, right? Inductor changes its polarity. Voltage
right?
polarity is changing. How can you fix
Right?
the convention?
Why can't we? It's in your hand, right? Every books has been written based on that convention and assumptions. Why can't
Yes.
you?
Then if I take VL is equal to V naught, then graph will not
Oh,
be valid.
okay, okay. See, we
Sir,
will take this discussion at the end. Okay.
no, this is the important point, right? If you take it at the end, what is the use? This step is missed out.
So okay then, I am not
Sir,
able to convey this topic, so
sir,
I don't
Rahul,
think I will be able to convey this explanation. So if you can wait at the end, then it would be great. Otherwise, you may discuss it with other mentors. So during off period, we took the value of VL, that was minus V naught, and during on period it was V in minus V naught, and this time stamp was dt, and here it was t, right? And it can go further as well. With every time period, it will be repeated. Now, as we have drawn the voltage waveform, now we can easily judge the inductor current waveform. So, when it will see, let us assume inductor has some initial condition. So, it will start from some particular value and it will discharge to the same value. So, as we know that average voltage across inductor in a one time period will be zero. I don't think any doubt should be in this statement,
yes,
and this thing should repeat after every time period. So, if you have to compute the value of gain, the relation between input and output, okay, so that we can apply the volt second balance and we can compute. This expression will give us the value of gain, that will be V naught by. So anyway, this t will be zero. So from 0 to dt, VL had the value of V in minus V naught dt plus dt to t, it will be minus V naught into dt equal to 0. And if you integrate it, you will get V in minus V naught into dt plus minus V naught into 1 minus t into t is equal to 0. And you solve it further, not 1 minus d into t, this t will be cancelled, and you will land to V naught is equal to V in into t. So d is the ratio of the duration of turn on period of the switch. The switch, I mean this switch, not diode. Okay, this will be turned on for dt, and the remaining time the diode will take. So its turn on period for the diode will be 1 minus d into t. So you have computed the value of gain V naught by V in, that is d. But this will be true only for the continuous conduction mode. What I mean by continuous conduction mode, that your inductor current waveform, it should not be zero for a finite duration, right? So let us suppose if your inductor has a smaller value, and due to that this current is falling earlier before it is completing the time period, and it will be zero for certain period, that is known as DC, discontinuous conduction. So it is also very important topic that we might look up, but as of now we want to see certain other parameters that would be helpful in terms of problem solving and all. So this was related to your V naught by V. Now you know the value of V naught in terms of input voltage, and after that, if you want to know, if you can see you know uh, the inductor waveform, so you may be able to observe the ripple. This is called the ripple in inductor current, and this ripple can be reduced from the design of proper inductor. What I mean by proper inductor, the required value of inductor to reduce the level of ripple current up to your desirable level. So whatever the value of ripple current you want, according to that, you will have to compute the value, and then you will get the parameter of inductor, and that you have to connect in the circuit. So again, we will apply VL is equal to L di by dt. Okay. And since here it is finite period, and you assume for any time period, right? Either you take VL on, VL value during on or off, doesn't matter. Just for the convenience, we are taking VL on. That will be L DIL on by dt. On, right? So your inductor current is changing by del IL, right? For finite time period. And this is the ripple in your inductor current. And dt on is your t into t. T is time period and d is your duty ratio. So that much time your switch will be turned on, and during that period, what was the value of inductor voltage? That was V minus V naught. So from this expression, you can compute V in minus V naught into D into T by L, and that you can write as V in minus V naught by S. So this is the value for the ripple across the inductor current. This is also very important to compute the ripple current because it is very frequently asked type of problem. And the next parameter is ripple in your output voltage. That is nothing but the capacitor voltage. So if you want to draw, so how to compute the ripple across your capacitor or output voltage? So let us assume, let us see this circuit first. So whatever IL is here, that will go in capacitor as well as load. Right? So if your IL will have, see, basically, if I will tell in broader perspective, this capacitor is just to, you know, it will enable to flow of only ripple current, delta IL, basically, and whatever the average value of inductor current, that will go to the load. So, and that should be DC because we want DC current at the output, and in output, the flow of current should be pure DC, and that will be allowed by this capacitor. It will filter all the ripple that was coming through the inductor, and it will allow the flow through the capacitor. So due to that, capacitor will get, certain charging discharging kind of phenomena, and after that you will have your a smooth DC current at your output. If I plot here IC, since this was the plot for IL, right? So, if you will compute some average value, it will have I naught, and from this triangle also you can compute the value of IL. First, you take this reference, and after that, it will be the area of this triangle divided by time period. That will give you the average value of the inductor current. So, we were discussing about capacitor current. So, this capacitor current will be shifted by I naught, right? Uh, from the KCL, IL is equal to IC plus I naught. So IC will be IL minus I naught. So if you reduce the term I naught from this circuit, you will get the value of your capacitor, and it will repeat with every time period. This is your PT. And during this period, the positive IC, this is IC, and if you connect it further, we can apply the charge balance. So whatever the charge it is getting charged by during this period, this will be some time stamp and it will be other time stamp, and during this time period, generally it is not convenient to compute these time stamps. So what we do, we compute the charge stored here, delta Q, and if you divide the, you know, the Q is equal to CV, right? So delta Q is equal to C delta V. So the level of the voltage ripple and the level of capacitor, as you see, if you increase the cap size and you have the constant charge, then your value of voltage ripple will go down. So that's another way of seeing the value of capacitor that affects the voltage ripple, right? So let us assume, or rather, let us compute delta Q, right? So delta Q will be delta Q by delta T is I, right? So it is delta IL by 2, and this is IL by 2. So this delta IL by 2, I see. If you compute area, that will be delta IL by 2, and if your charging and discharging have the similar slope, in that case, this time stamp would be generally d by 2 into t, and here dt and t. So let me compute t minus dt divided by 2. So 1 minus d by, sorry, t plus this time stamp would be dt plus dt by 2. So 3 dt by 2, dt plus this dt by 4, I guess. Dt,
Yes, sir. If it is 0.5 duty cycle.
sorry, I can't hear you.
Sir, this first timestamp is dt by 4, uh, not t by 4.
T by 4, yeah, yeah. T by 4, it will be dt, it will be 3t by 4. It
Sir, it
should be,
doesn't make sense then. Meaning, then we are considering 50% duty cycle. Why
yeah,
should
yeah,
that be?
yeah. Just
That is
give
not
me
correct.
a sec. Just give me a sec.
No, IL can be calculated. The slope can be calculated of current slope can be calculated with the help of voltage, right? Voltage and time.
Yeah, yeah, that's another way. That is true. IL can be calculated as VL V in minus this voltage level divided by inductor. What you are saying, right?
Yes.
Yeah. So if you consider this slope, this was for IL. So this slope value. Okay. So first, let us compute the slope value. So let us. We have this kind of characteristics of inductor current, and during charging, it is facing V in minus V naught by L. That will be your di by dt, right? Here, since it is falling, so minus V naught by L. So, and if you apply, just give me a second, I need to verify it.
Sir, actually, at that time, we were trying to do the charge balance, right?
Yeah, yeah.
But finally, we are ending up at volts second. What now we are doing is,
No, no, it is related in some way. That's what I am looking right now. So, basically, what we do, Q is equal to CV, and Q is again, the rate of change of current. So that what I am seeing, that where that relation is present.
Yes. Del Q can be written as C times del V.
Yeah, yeah, you are correct. Just give me I have prepared this derivation. Yeah, so in meanwhile, you can also suggest something till I am looking at.
Sir,
Yeah, I'm here only.
sir, by doing that charge balance, what we are intend to do, sir? The
We
charge
are intending to compute, our ripple in voltage. So basically, ripple in voltage, either you can compute from charge balance or you can compute it from capacitor current. Actually, I heard it.
sir,
Yeah.
uh, if we take that current waveform through the capacitor,
Mm-hmm.
we are subtracting the output load current from the inductor current so that we are getting the capacitor current.
Correct, correct.
So the area under the positive capacitor current is the change in Q, right?
Uh-huh.
Because that is the Q entering the capacitor.
Yes. Actually, during that period, our capacitor is getting charged. Okay. So I'm just looking for the relation that it has with the, your ripple voltage that I missed somewhere. Actually, I did not prepare for today's lecture. Today is holiday. But okay, just let me search.
Sir,
Yeah, go ahead, please.
so when we look at that area under the curve,
Uh-huh.
we are from going from dTs by 2
Mhm.
to 1 minus d into ts by 2, right?
Yeah.
So
Uh,
so the length of the base will be ts by 2.
the thing is that we cannot directly assume d is equal to half, right? If you are saying that it is dts by 2, then you are
So,
assuming d as half, right?
huh.
Yeah. So anyway, let
No,
us.
but if the current is same and the positive side, I mean dt delta IL by 2 top and delta IL minus on the
Mhm.
bottom, then definitely it has to be that way, right?
Yeah, yeah. So what I think is delta Q. It
So
will.
it is half of DTS by DTS only. We are not saying about the duty cycle being 50%. We aren't saying that.
Yeah, yeah. We are saying dts by 2, right?
Ah, correct. That's
Yeah.
where the zero crossing will take place,
Uh,
positive going, and negative going will be 1 minus D into TS by 2.
yeah. So this is you are saying dts and dts by 2, and this is you are saying 1 minus d into ts by 2.
So so if when you draw the current across capacitor, the intersection with the zero axis is what I'm talking about, x axis, because we
Mhm.
shifted by IL, right?
Yeah, we shifted by 90 degrees. So okay, let us try this approach and see where we land. So del q is,
Excuse me.
yeah,
Here, I have there is no effect of RL.
RL, you mean load?
Yeah, load resistance.
Yeah, yeah,
If load
that,
resistance has no effect, then we can assume that it is a DTS by 2.
mhm. Yeah. So as of now,
It is the
for time being, we are considering it is V not just for R or RL kind of load. If it will have some battery kind of thing, then scenario will change a bit. Okay. So we will
Sir,
apply this. Yeah, yeah, go ahead, please.
sir, the bottom time span that we are using for positive or negative current,
Mhm.
so that should be DTS, right? It should not
Yeah,
be.
actually, the thing was we focused on this time frame. The earlier person who said that, yeah, this period we can easily know, but timestamp we can't determine, right? Because it will be depending on certain other parameters. So if we know that we know that it is turned on or this period it is by 2, right? You are saying something else, Muthu Kumar?
No, sir. I think
Sir,
I don't know how DTS by 2 will come. Okay, sir.
Okay, okay. So see, uh, okay, how to separate it? So
sir, if we draw the waveform of the current,
yeah,
then so if we say that the on time is DTS, right?
on time it is correct.
So half of that time the current through the capacitor will be on the negative side, and half of the time it will be on the positive side. We aren't saying that duty cycle is 50%. That is
Yes,
irrelevant to us.
yes,
Now, when it goes from DTS to TS,
yes,
in the same way, it has to be half of the time of that duration on the positive side and half of the time on the negative side. So that then only the ampere second principle or relationship is equal to, I mean, the current flowing through the capacitor is zero. That's what we are assuming, right? Like we assume to the inductor
uh-huh.
voltage to be zero average.
Mhm.
In the same way, we can say that the ampere second
And
relationship for the
mhm.
capacitor or the average current flowing through the capacitor is zero. That's what we
Yes,
are trying to say, right?
yes,
So here, the zero crossing that we are having, when the current is going positive, that intersection is dTs by 2.
Okay. Yeah.
And
Yeah.
the
That.
peak is at dt. Yes.
Yeah.
Peak is at
That
dTs.
it is. That
And the
is that.
negative. Uh,
Just hold on for a second. So I hope
Sir,
if
this is the
it is
this
is
is
there any
true.
object? Yeah.
This is true when both slopes are same. Slope is different, then it cannot be dTs by 2.
No, no. See, the thing is, it is this slope would be same, right? This slope and this slope both will be same. That you agree?
No, yeah, yeah. I'm talking about that falling side.
That falling side, now we will focus on the falling side. So if you find any discrepancy now, then we can discuss it further. So see,
Okay.
this period is 1 minus d into t, right? 1 minus d into t. So this falling side slope, where it is, so actually these are not aligned both waveforms. So let's assume, let me align it. So the falling time duration, let us assume till this period t, it has 1 minus t into ts, the total time period, right? From this point to this point. Let me denote it with different color. From this point to this point. Now can we say this is 1 minus d into ts by 2? Not time much time, but this period,
yes, we can say that.
1 minus d into ts by 2.
Yeah.
Is there any objection with this point?
Sir,
No.
not that
If
range, but that particular, the third.
now that particular time stamp we can compute easily now. You see, uh, we can add dts, this point is dts plus this time period, right? Plus 1 minus d into ts by 2. That will be this point, we can say t dash. Can I write it like that? T dash is equal to dts plus 1 minus d into ts by 2. And now if I will simplify it, so it will be ts by 2 plus, dts minus dts by 2, so dts by 2. So it is coming out to be 1 plus d into ts by 2. So this time stamp t dash is now 1 plus d into ts by 2. Is it fine?
So what will happen if the slope is not 45-degree? It is different.
Slope is not 40. Yeah, it is different. Okay, so you mean to say, so see,
Suppose slope is very fast,
okay,
60-degree.
I understood your
Will it
point.
be?
Yeah, so you want to say if slope is kind of this, then what will happen, right?
Yeah, very sharp.
Yeah, yeah. Just let me again draw the waveform of both, because whatever the inductor, my one sentence answer for that question, uh, definitely I will explain it with graphs. But the one sentence answer is for that question is whatever the inductor current waveform that will follow to the capacitor current, we are just reducing average value from that graph, right?
Mhm.
So let us verify with graphs as well. Let us assume we have, again, this
Sir,
is, yeah,
sir, actually we are more concerned about the area here, right? Positive
yeah.
area and the negative area. So
Once we know that,
we don't need to consider on the slope, because whatever the slope might be, because since the waveform is symmetrical with the horizontal axis, the
uh,
area and the positive and negative area will be equal. So we
equal.
don't need to be concerned with this slope.
No, no. See, that you are correct. You are definitely correct. But the thing is, we are computing this time either to compute positive area or negative area. Right? So if we know this period and this half period, but we do not know this half period and this half period separately. So that's why we need to compute this T dash and let us assume T1 and T dash. So if we know the T1 or T dash minus T1, then we can compute this area, right? Otherwise, how you will compute that area?
We know the length, right? Now we know that the first intersection is dts by 2 or dt by 2, and the
Now we
second
know. Now,
intersection is 1
yeah,
minus d.
I agree with you. Now we know. Now we know. So that my next step is just to compute the area. Before that, I want to explain his or her question. Who asked like, what will happen when the slope will be solved? So that's what I am trying to justify with. If you will reduce the average current, you will get the same. See, this expression is not the function of the slope. This expression is the function of how much duty cycle is there. Your duty cycle is less, then you will have, this value will be lesser or higher, right? So let me just plot it for you once you, I think, be able to guess, right? So if this kind of slope is here, both are matching. So let us assume this is again your TTS and this was TTS by 2. So 50% of the slope, I mean in terms of line, this 50% will always lie above the x-axis and 50% will always lie below the x-axis. Similar is true with the negative side as well. How much the slope of the line, it doesn't depend on that, right? So this time stamp will be again the same, 1 plus b into ts by 2. So let me write it, and it will always be ts. No, doesn't matter how much slope of your line, because it is just the derivative of your inductor current. So the way inductor current behaves, the same way your capacitor current will behave, or it has to behave ideally. So I hope that might have answered your question.
Yeah. Yes.
Yeah,
Sir,
thanks. Yeah, go
sir,
ahead,
actually,
please.
yes, sir. It is understood, sir. Actually, if you write this as DTH itself, even though this DTS is less than TS by 2,
Uh,
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 that will be
TTS is
common.
less than TS by 2, you are saying.
Yes, sir.
But that is not generally true, right? That might
Yes,
be
sir. It
true,
is.
but
It is not true, but
hmm,
we can write it as DTS because that will be compensated by this del IL, no? Because if this reduces, this del IL will increase, but by
if
two,
you,
del IL by 2.
that is true, yeah. If you reduce DTS, then your LIL by 2, yeah, that will reduce. Yeah, you
Sir, then we can come. Then we don't need to write this timestamp, right? We don't need to compute this. Just we can write half into del IL by 2 into TTS.
are. Half into del IL by 2 into DTS. But how you can say this DTS? Because see, you are saying when DTS, you are saying half into del IL into DTS, right? That's what you are saying.
Del IL by 2.
Sorry, del IL by 2 into DTS, right?
Yes, sir.
So when you are saying this expression, you mean to say half into del IL by 2 into DTS. DTS is this entire portion, right?
Yes, sir.
Yeah. So if you say DTS by 2, then you are again saying only one portion of discharging, right? You are neglecting the other portion of discharging. You got my point?
No, sir. I have said DTS.
Yeah, you said DTS, right?
Yes, sir.
That's what I told you.
Yes, sir.
DTS, in DTS,
Ah,
it is charging and discharging as well. But
yes.
we need to know either charging total charge stored during idle charging or discharging. You are when you are saying DTS, then you are combining both the reason, discharging and charging.
No, sir, not from zero. If we take from the first timestamp, it is again DS, right? From the first
Yeah, that
positive zero crossing of first positive zero crossing to the second one.
you are saying this area,
No, sir, the right side also combined.
this one,
Ah, total
both
J.
combined. Yeah,
Yes.
but you do not, you cannot say that this period is DTS, right? That's
Okay.
why we needed timestamp. No,
Because this, if D is reducing, this del IL will increase, so that area will remain same. Del IL by 2 will increase. If DTS reduces in this area, the
just
time
let me write your sentence. You are saying D is reducing, then del IL is increasing.
yes, sir,
Del IL by 2,
uh,
that you are saying.
will increase.
So,
So, so for computing this area, this the writing like half into del IL by 2 into DTS itself is sufficient. We don't need to compute timestamp. That is what I'm saying, sir. Is it correct?
okay, so I will have to think on that point. But what we can do after this session, you derive with this, and if we get the same answer with whatever approach we are taking and whatever approach you are taking,
Uh,
okay, and we will again discuss it in the next session, and or you can verify with certain standard books as well. If it is coming same, then your approach might be also correct. And in your mind, I think you might be thinking right, but I am just not able to get that it should be equal to DTS. So that's why I went ahead with computing the time step.
okay,
Right?
sir. I will check and come back to you, sir.
Yeah, definitely we can discuss this point. So I think we computed this DTS plus 1 minus T into TS by 2. So we concluded with this time period of positive charge. So now we will compute the positive charge. So delta Q is equal to half into delta IL by 2 into, you know, this time 1 plus D into TS by 2 divided by TS, right? So further, this TS and TS,
No, sir. That length is different, sir. It cannot be 1 plus D into TS by 2. We have the first zero crossing also.
yeah, okay, this DTS by 2 and this point. Ah, ha, ha. Correct, correct, correct. Thanks a lot. I think you are saying, or what I missed, T dash minus this T1, right? Thanks. Yeah. So that's the point. I think now 1 plus D into Ts by 2 minus dTs by 2. So that will be our uh, delta T. It is now Ts by 2. Is it right? dTs by 2 will get cancelled and it will remain Ts by 2. So apparently we did so many juggleries and we end up with this period as Ts by 2. So yeah, so now I remember this is the expression. Yeah, del IL by 8. So now this is correct. And what DT is? So yeah, oh,
Why TS by 2?
yeah. So let me explain it once again. So T3 we computed, right? So T3 is nothing but this point, T3, and we have T1 this point. So the period for positive charge, that is T3 minus T1, and T3 we computed as, where did it go? T3 here we computed that T3 was this DTS by DTS plus this period by 2. So T3 minus T1 is our value that is coming out to be TS by 2. So this was T3 and this was T1. So T3 minus T1 is, if you segregate all the thing, then DTS by 2 and DTS by 2 will be cancelled and you will be left with TS by 2.
Okay.
So that is our del Q, and del V will be nothing but del Q by C will lead to del IL by 8C, and del IL we computed already, right? So del IL was nothing but D 1 minus D L, right? 8FC. So this will be the value of del V. So uh, as you increase the value of capacitance, you will get the lower ripple in the voltage. So, just to clarify the confusion, all the confusions that appeared, you know, what happened, we needed to compute these two time stamps just to identify this duration. And once we got to know this duration, after that it was quite straightforward, right? So, if any doubt in this, you can clarify it once again. Okay, so if not, then I think we can see certain problems that has studied with me. I have a problem. So in this problem, the concept of discontinuous conduction mode has been checked. So we need to identify the value of D at the boundary of continuous and discontinuous inductor current. So what will happen at the boundary, and this parameter at the boundary, that boundary condition, it justifies that your converter is just continuous. So we can apply the all the conditions from conventional continuous mode operation and further we integrate and then we will see how to move it. So see, generally during
Circuit is
at uh, okay, circuit is not given. It is just your buck converter, whatever we just saw. So
okay.
let me draw it. Yeah. So this is your circuit, and you might have guessed. So just a quick tip to recognize the circuit, whether that is buck converter, boost converter, or which one. Generally, in buck converter, the average value of inductor current is the output current, right? So it it implies that your inductor must be connected nearest to the load. So that is a quick tip you can see, and you can pick that which circuit is that. Uh, at the boundary, this inductor current waveform would look like that, and it will repeat with every. It does not contain any initial value of current. Whatever the peak value of this waveform will be del IS. So the entire current is ripple current, and it is just getting continuous. So it will again start and it will go on. So we can write IL average will be half to del IL into T by T. So this T will be cancelled. So IL average you will end up with del IL by 2. So somewhere here we have IL average, and as I told just now that IL average is equal to I naught. So this is your I naught, right? Now we have I naught and we have IL average, and we know the expression of del IL in terms of our V in and V naught. So you can equate both the equations. So this time I will take the off condition. Last time I took the on condition. This time we can take the off condition so that we can justify that it is same for both the time period. And during this del IL, again you will apply the voltage equation across the inductor. VL off, that was minus V naught, and it is equal to L del IL by during off period, since we are talking about, so by T 1 minus D into T. So now del IL you have 1 minus 3 into V naught by F, sorry, yeah, F, yeah. Since T will go on numerator side here, so F is nothing but 1 by T, so F will come in denominator. Now we have del IL, we can equate it to 2 into V naught by R. Are you wondering where this comes from? Is it fine with you? 2 V naught by R, del IL, from this expression. We just said that I naught is equal to IL average, and IL average in the case of boundary condition is equal to del IL by 2, that we can concluded from the area of that triangle, right? So after that, since we have equated, we can easily cancel it out, and we will get the value 1 minus D is equal to 2FL by R, and this is the value of your boundary condition, that will be 1 minus 2FL by R. So This is a derivation as well, and this is a question also. Is there any doubt in this problem? Yeah, just give me a second. Actually, I am having a meeting. Yeah, so we may proceed with some other problems if we are clear with this issue. So it's better we should move ahead with another converter, that is boost converter. Yeah, so here the circuit, here I am mentioning it already. Uh, yeah, what about DCM mode of operation? Yeah, so DCM mode of operation, I am thinking to combine all the DCM mode of operation at once when I am finished with all three converters. Or do you want me to discuss it right now? That is also fine with me. I can start with DCM mode of buck converter as well. So, uh, it is, should I move ahead with DCM mode of buck converters? Okay, so we will discuss DCM mode of buck converter. Yeah, so
Sir,
we
can we
just,
go to previous problem?
right,
Previous problem.
just a second.
Sir, it is minus V naught, right?
Yeah,
Off
yeah,
condition.
yeah,
Then
you are correct again. Yeah, minus
then
V naught if you take, but it does not change the magnitude of slope, right? That we know that this is negative slope, and this is nothing but the slope, right?
yes.
Yeah, del IL
And
value. If you observe from waveform, I you can write it negative. Yeah, I have no problem in writing negative. You can write negative.
then expression change boundary condition is going to be 1 plus minus 1.
Oh, you mean to say this minus one plus?
Yes.
Yeah. Now you, if you will compute from this expression, you will get negative duty ratio.
Mhm. Okay.
Okay.
So you don't have to consider negative sign. It is considered as a negative slope.
Yeah, from graph you can physically visualize, right? This will be del
Mhm.
IL. If you can
Mhm.
see, either you write negative or positive. What is making more sense? And it will be more confusing in buck-boost converter, where you will see many a times, and on that particular circuit, different authors has different perspectives. So some authors will take output voltage as positive, and some authors will take output voltage as negative. So it will be like very confusing if you will be stick to the either expression or circuit or graph. You have to visualize and you have to be comfortable with everything. What is making more sense here? If you see in that way with the problem or the circuit, then it would be easier for this kind of circuits. That I can say from my experience.
Okay, sir.
So just to start the discontinuous mode. So what I was telling that we just covered the boundary condition. We just saw from the problem that what happens at boundary condition. and that expression also we computed, right? So after that, what will happen? That we will see. So just let me plot the graph. It is really important to plot the graph for all the circuits every time. So during DCM, your inductor current will be zero for particular finite time, and it will again. So this is your T now. This is your dt, and this we can say as alpha, and this period alpha minus t into t becomes, or you can say from the textbook reference d1t. Now, if you plot the graph of voltage based on your inductor current, generally we draw voltage only, but since we are defining the discontinuity in terms of inductor current, so we will see when inductor was charging, our circuit was having the voltage of V in minus V naught, and when inductor was discharging, minus V naught, and it will remain zero for certain period. That is nothing but our this also we can define. This is nothing but dt plus d1t. So t minus t plus d1. So t minus t plus d1 into t. So that will be 1 minus d plus d1. Right? So now again, if you want to compute your output voltage and input voltage, ratio. This is sorry, this is VL. The gain value V naught by V. You have to apply the volt second balance. Volt second balance is nothing but the average value of inductor voltage is zero. VLDT is zero. That implies from zero to dt, you have VL as V in minus V naught dt plus dt2. What is this? Yeah, d plus d1t, right? D plus d1t, that is minus V naught to dt. Now, if we simplify V in minus V naught into dt plus minus rather d plus d1 minus d to t equal to 0, that will be equal to V in minus V naught to d is equal to V naught to d minus d will be cancelled out. So V naught into d1. So V naught into D. dV in is equal to V naught D plus D1. The ratio will be V in D by D plus D. Okay. So in this continuous conduction mode, your ratio has been changed by certain parameters since we introduced D1 because of discontinuity. So what the change you are able to observe from this expression only compared to the continuous conduction mode.
The output voltage is even more lesser.
Output voltage is lesser. That's what you are saying
Yes, sir, compared to that previous expression.
previously. Okay. So let me write it. This is for DCM. For CCM, our gain was V naught minus V in. That was D, right?
Yes, sir.
Now you observe it once more.
Sorry. Definitely in DCM, the output voltage is lesser compared to the CCM.
Okay, you are saying definitely, so we'll have to think it. So you just see the graph. Let me bring back the graph for you once. Hmm. Now you can see D plus D1, dt plus D1t is less than T, right? So let me write it for you.
Yes.
So D plus D1 to T is less than T. Okay. What it implies? D plus D1 is less than T.
Yes.
If it is less than 1, then it should be intuitively greater than, right? If D is divided by less than 1, some X, let us assume 99 point, it will be something 1.01 times D, right? So it will be more, right?
Sir, actually, the denominator also has D, no?
Ah, it has D, but the thing is here it has the parameter 1 and it has D plus B1, which is less than.
Okay, sir. If the denominator is 0.9, then the numerator will be less than 0.9.
Okay, let us
I think
assume
whatever be the D, since at the denominator there is a D also, so it will be always less than 1.
uh, which one for DCM you are saying?
See, and DCM, V naught
Yeah,
upon V in will be always less than 1.
yeah, D plus D1 will always be less than 1. And
No, V naught upon Vi in ratio, that is gain is always less than 1 in case of DCM case,
yeah,
because the expression is D upon D plus or D1.
yeah, that is for sure. Since it is a buck converter, the voltage at output will be less than input. So V naught by V is definitely less than 1. I am not talking about that thing. I am talking about this V naught by V in, V naught by V in during DCA is less than or greater than V naught by V in CCA. My question is
Hmm.
this. Yeah.
Okay.
Yeah, sir. What you have written is correct. DCM is less than CCM.
But I have written it wrong. It is other way around. And let me write the gain values as well. So the gain value that we computed for DCM, that was D plus D divided by D plus D1. It is greater than D. You do not agree with this expression? Okay.
How D upon D plus D1 can be greater than D?
The point is, the catch here is D plus D1 will, let me show you the waveform once more. This is dt, right? Sorry. This is dt. This is d1t. This period is already written, and t is after that. So dt plus d1t plus that period that I have already calculated, 1 minus d minus d1 into t, that will lead to t. Right? So this additional term has to be added to get equalized to t. You got my point, or you have still some confusion?
Yeah, yes, this is I understood, sir.
Now, so if it is equal and we are reducing this component from all the things, so it will be less than t, right? dt plus d1t should be less than t, right? And further, it will lead to d plus d1 is less than 1, right?
Yes, sir.
You agree till this point?
Yes, sir.
Yeah.
Yeah. So if d plus d1 is less than 1, and since we are dividing, it is less than 1, then whole term will be higher. 2,
Yes.
yeah. So now I think it should be fine.
Yes.
So that is one, you can say, advantage as well, that with the same duty ratio during DCA, your voltage is bit increased. So let us see about other things, that what is happening with our ripple current. So or average value of inductor current. So IL average now we have to compute. So let me bring, let me redraw it. So this is your T now, dt T plus T1t, and the rest what? 1 minus T minus T1. So what will be IL average? It will be area, and this peak value is del IL. So half into del IL into T plus T1 to T divided by 2. So half del IL T plus T1. So this is your average value of inductor current. Now to compute average value, you must have the value of D1. Okay. So that D1 you need to compute in terms of D. So that will lead to certain equations that I will derive. So just uh, bear with me for the derivation. So now IL we can write as I naught. So I naught is nothing but V naught by R if the load is resistive, and IL we computed del IL by del IL by 2 into D plus D1. I am just putting this expression here. That is nothing but equal to V naught by R. Again, this del IL, if we want to compute in terms of off condition, minus V naught into this. Sorry, let me write the proper inductor equation. L off is equal to L LIL during off condition. This time during off condition, we will consider only this period, D1 period, right? So I can write D1 period. And now the D1 is not is equal to 1 minus D. That is something different that we are trying to compute in terms of D. Now LIL is equal to, and VL off during the off it was minus V naught. So del IL is now V naught into D1 divided by F. So that I will put here. And again, since we are talking about vehicle, so we have to ignore this negative sign. So D1 V naught by FL into D plus D1. And this 2 I am bringing here is equal to V naught by R. Fine, till this point, any doubt, any confusion, any messed up thing? Okay, so if we followed till this far, so now we are just one step away. V naught is getting cancelled here. We will have to form a quadratic equation equal to 2FL by R. And it is now D1 square plus DD1 minus 2FL by R equal to 0. Now we can write D1 as minus D plus minus D square minus 4AC, so that will be minus 4 into minus 2, so 8 F L by R divided by 2. So minus D minus something, so obviously that will lead to negative term, and that is not possible for duty ratio, so we will have to ignore the minus sign, so we will be left with this expression. Now you can write it as D1 as D plus D square plus 8 L by R divided by 2. So this is your D1 in terms of D. Any doubt in this? If not, then further I can write as V naught, since we derived V naught by Vs as D divided by D plus D1, and at the place of D1 you plug in that value minus D plus minus D plus D square plus 8 by R divided by 2. Someone's mic is on, so you need to turn off please. Yeah, so this is the gain value. So now you will be given with frequency and inductor and resistor. Then you will be easily able to compute the gain, that is V naught by Vs, even in the case of discontinuous conduction mode, right? If you know this expression, you do not have to verify with graph and all. If you know this expression and if you are asked only this parameter, that is V naught by Vs, right? So I hope you understood the concept of discontinuous conduction mode for buck converter. In the next session, we will start boost converter and buck boost converter, and we will see the discontinuous conduction mode for them as well, and further we can solve certain problems.
Sir,
Yeah, you have doubt? Muthu?
sir, sir, can you please explain again that how the gain of BCM is higher than CCM?
Okay, that one, yeah, definitely.
Yeah, BCM.
See, you got this point from this curve. Sorry, let me.
My doubt is here is,
Hmm. You are able to see this triangular graph, right?
yes,
Yeah. So this node is d plus d1 into t, right?
yes,
And
sir.
this node is t. So which
Yes, sir.
is higher? D plus d1 into t or t?
T,
T is higher, right?
yes, sir.
So I can write d1 plus d into t is higher than, sorry, smaller than t, right? And
Yes, sir. This is okay.
if, this is okay, yeah. So d plus d1 is less than 1, right?
Yes, sir.
It is also fine. Now
Yes,
you are saying that you are not okay with this term,
yes, sir.
that d by d plus d1 is how higher than d. You are not okay with this term, right?
Yes, sir. Because I think because in the numerator we are adding the same number d and we are adding with d1. So
Hmm.
anyway, this d plus d1 is always higher than the numerator. So this
Yes, that
total
is
term,
true. That is true. See,
okay,
the thing is you are getting confused with, you see d plus d1 as a different. Whatever the value in numerator, you are saying correct that if this d will increase, this d will again increase and whole term will increase. But there will not be any case where d plus d1 will be greater than 1, right?
yes, sir. It will not be greater than t.
It
Yes,
will never be greater than 1.
yes,
So if it will never be greater than 1, then this d, if it is always less than 1, if it is always less than 1, let us assume 0.99. So isn't it greater than d?
sir.
Yeah.
I don't know, sir.
Okay, so what you do, you think
This
over
is
it
correct.
for, yeah. So you think over it for certain amount of time, like 5-10 minutes with cup of tea, and then you will get why I am saying this. Suspect. Okay,
Right.
so yeah, so you just go through this and you just think over it, and you will get the answer. And in next session, I will ask you whether you got it correctly. You have asked two questions. So one question you told about that. DTS, right? DTS by 2. So that you verify with that DTS by 2, and
Ah,
this question D plus D1 is
okay,
how less than 1. So you
okay,
think
sir.
over these two problems and we will start with these discussions only.
Okay,
Okay.
okay, sir.
Okay then. So thank you everyone for attending, and I am really happy
Can you
that
explain the doubt, sir? Can you explain the doubt, sir? I'm waiting.
oh, okay. Yeah, sure. So that doubt in the starting. Yeah.
Sir, a general concern. Sir, it
Yeah.
would be helpful if you upload the video the next day itself. As we are all learning through the uploaded videos only, we are not able to attend the all live interactive session. So we have assignment due tomorrow, but yesterday's live video is not at all uploaded till now. So the main
Oh,
objective of having live interactive session is to get some idea to solve the assignment. That's why we are attending the live session. We are unable to attend the live session. If the video is uploaded in prompt time, it would be helpful for us to solve the assignment. But
see,
yesterday's video is not at all uploaded till now. But we have the assignment due tomorrow. Then what is the purpose of having live interactive session?
okay. So for
Yeah,
part
this is
two,
also the problem for me.
yeah, definitely I understand that.
Okay.
And for part two series, I am doing the same. I am uploading the same day within half an hour. So
Thank you,
Oh,
sir.
thank you.
But
but
even though I have raised the concern in discussion forum, I have
mhm.
not at all getting any reply. That's why I have coming online, particularly to insist this.
Okay, okay.
Thank you,
So
sir.
for my session, you rest assured that I will upload within half an hour. But for
Thank you,
other
sir.
mentors like Saptarisi who took yesterday's session, so he sits in my lab. I will push him and I will tell him today that to upload today itself, and I hope he will upload it by today. And regarding another mentor, I don't know him personally. He's from different institute. So I think it is better if you remind him by mail because every week I do my part, but I cannot guarantee for others, right? So
Okay, sir. Friday's mentors
okay,
video is uploading, getting uploaded on Saturday, but Monday, yesterday's session is not at all uploaded till now. And we
okay,
expect to watch the videos for solving tomorrow's few assignment.